Hi everyone. After looking through exams, I just thought it might be helpful to go through the exam graphing problems. So that's what we're going to do in this video. Okay, so let's start with this one. So we have y is equal to -4 cosine of 3x plus pi over 2. Okay, and so we're going to identify all of the key attributes and then we'll graph a period of this function. So one thing you might want to do when you approach a problem like this is start by labeling the key values that you see, the key constants you see in the function. So specifically what I mean by that, the -4, the 3, and the pi over 2. Let's label those in terms of our standard variables that we see whenever we graph a function of this form. So a, we're going to call that -4, we're going to call that a, so that's going to be the variable a. Okay, we have something in the place of b, so that would be our 3. We have something in the place of c. Now, here we need to be careful. So c will be the constant that's added or subtracted, but when we look at the standard general form for whatever we graph in terms of a trig function, the general form is going to have subtraction inside of the trig function. So that means when we see a plus sign, we need to think of that as subtraction of a negative. So whenever we have an addition sign inside of our trig function, the actual constant itself will not be a positive constant, it will be a negative constant. And that's going to make a difference when we get down to graphing, so it's important to be careful with the signs there. And again, just to reiterate, whenever we see the general form for a trig function that we're going to graph, we have subtraction inside of the trig function, so addition we think of as subtraction of a negative value. Now, in the general form, we also have a variable d. D will be added or subtracted outside of the trig function, but notice in this case we don't have anything. So that means d is automatically going to have a value of 0. So what do all of these different constants mean? Well, each one of these represents a potential transformation to the original graph of the cosine function. So the a out front, we think of that like a vertical stretch or a vertical shrink. When we're talking about trig functions, though, that's called the amplitude of the trigonometric function. So the amplitude just tells us how high and how low we're going to go from the center of the cosine graph, from its central line, which is typically centered there on the x-axis. So in this case, the amplitude will always be the absolute value of whatever a is. So the absolute value of -4, which will be 4. Okay, so that tells us how far we go above the central line and below the central line when we graph this cosine function. Now, what does the negative mean? Well, if you were to think back to how you graphed in college algebra, anytime you have a negative multiplied by your function, the negative is going to generate a vertical reflection. So not only do we have a stretch, not only is our graph going to be taller than it otherwise would normally be, we're also going to have a vertical reflection. So I'm going to make a note of that. We want to keep that in mind as we graph. Okay, now B is going to relate to the period of the function. And period, if we're going to put that in the context of perhaps how you graphed in college algebra, we think of period as relating to a horizontal stretch or shrink. In other words, how far do we have to go from where one cycle of the function starts to where it ends? Now, the standard period for the cosine function is going to be 2 pi. That means we complete one cycle of a cosine graph over the course of 2 pi units. What this 3 does is it ends up shrinking our period, or just changing it in general. So the period will always be defined as the original period for the function, whatever that happens to be. In this case, it's going to be 2 pi. And it's going to be divided by whatever that value is for b. So in this case, 3. And then sometimes when you do this division, it will result in something that needs to be simplified. But as of right now, this is a value that can't be simplified. So what does this tell us? This tells us that in order to complete one cycle for our graph, it's going to take 2 pi over 3 units horizontally. Now the phase shift, that's another name for a horizontal shift, so left or right, that's going to result from our c. Now we have to keep in mind that not only are we shifting, but we've also taken the standard period and shrunk it by a factor of 3. So however we shrink that standard period also affects how we shift left and right. So in generating the phase shift, we're going to take our value for C, which in this case is negative pi over 2, and we're also going to divide that value by 3. So not only does that 3 shrink the period, the overall length of one cycle of the graph, it also shrinks the amount that we're going to shift, in this case in one particular direction. So what do we do with something like this? We have a fraction inside of a fraction. Well, remember fractional division, we can change that into multiplication by the reciprocal of the denominator. So dividing by 3, same thing as multiplying by 1/3. And so then we can just multiply straight across. So our phase shift is going to be negative pi over 6. And in this case, the negative, what does that tell us? It tells us that we're shifting horizontally to the left in the negative direction. So how does this follow what we see in the actual function? Well, if we see addition, that means we're shifting in the negative direction. We're shifting in the opposite direction. If we see a subtraction here, that would mean we're shifting in the positive direction. So that's just a good general rule of thumb to remember in terms of what's happening with those phase shifts. It's always going to be opposite the direction that the sign gives you. So if there's an addition sign, we're shifting to the negative direction, the left. And then if there's a subtraction sign, we're shifting in the positive direction, in other words, to the right. Okay, now the vertical shift, shifting up or shifting down, that would come from adding on or subtracting a value outside of our function. And in this case, that is 0. We don't actually add or subtract any value onto our function. So for vertical shift, I'll just put none. So this gives us all the information we need about what's going to happen to this cosine graph when we put it on the coordinate plane. But how do we actually put all of these different features together, specifically the horizontal components? How do we actually put all of that together so that we have an accurately labeled graph? Well, that's where generating the cycle, knowing where the graph is going to start and where it's going to end, based on how the period looks and how the phase shift looks, that's where knowing what that cycle looks like is going to be helpful. So the standard cosine period, if we were to just graph a basic cosine function, that's going to go from 0 to 2 pi. If we were to graph just one standard period of cosine, generating the values from the unit circle, we start at 0 and then we end at 2 pi. Okay, so the input for the cosine function, the argument, what we would call the argument for the cosine function, normally goes from 0 to 2 pi. So we want to know, what do these values of 3 and pi over 2 do to those standard endpoints of 0 and 2 pi? So we're going to set up an inequality that simulates what the normal parameters are going to be, limiting our input for our single period. And then we're going to apply that pi over 2 and that 3 to those endpoints. So our standard cycle goes from 0 at the left end, and then that's going to be less than or equal to the input for our cosine function. And then our standard period ends at 2 pi on the right end. Okay, so the question is, we're now graphing in terms of x. So we have some different things that have been done to our x. How do these different things being done to x affect our endpoints of 0 and 2 pi? So that's what we're investigating at this moment. So I want to solve for x to see how these two values affect x and specifically its endpoints. So I need to start by subtracting pi over 2. So I'm going to subtract pi over 2 from both endpoints. So 0 becomes negative pi over 2. And then if we were to take 2 pi and subtract pi over 2, that's going to take us to 3 pi over 2. Now if you need, remember you can think of 2 pi as being the same thing as 4 pi over 2. And then you could subtract the pi over 2 from that, again generating 3 pi over 2. Now we also need to divide out that 3, and essentially what we see right here when we divide the 3 is exactly what happened in terms of the phase shift. If we were to take negative pi over 2 and divide by 3, just as we did above, then that's going to give us negative pi over 6. So negative pi over 6 is going to be our left-hand endpoint. Now, what happens when we divide over here by 3? Well, if you already have a fraction and you're just dividing, you can also just think of the value you're dividing as going into the pre-existing denominator for that fraction. So if we end up with a 3 in the denominator, and there's already a 3 in the numerator, well, those 3's are going to reduce down to 1, which leaves us with our pi and our 2. So our new right-hand endpoint will be pi over 2. So this is actually very important information. This tells us negative pi over 6 will be where our cycle starts, and pi over 2 will be where our cycle ends. Now, what that doesn't tell us is what's happening in the middle. In other words, how are we transitioning from key landmarks on our graph one to the next? And this is where we break down our period into our 4 standard units. So remember, when we graph, we're looking for 4 major units, 4 major locations, specifically because we think of the unit circle as having 4 quadrants, and we start and we cycle around and we hit 4 key landmarks. So in terms of how we're doing this, how we're dividing up our graph into key units, this is related to our period. We're taking the period, in other words, the length of the cycle, and we're dividing that period, that length, by 4. We're dividing it into 4 even parts because there's going to be 4 key locations that we see on the cosine graph. So let's see what this is going to be. So again, we're dividing a fraction by another fraction. We can change that into multiplication by the reciprocal. And if we want, we can go ahead and reduce that 2 and 4. That may be helpful. So that's going to turn this denominator into a 2. And then we can just multiply straight across. So that's going to give us pi in the numerator and 6 in the denominator. So pi over 6 what? Well, pi over 6 units apart. In other words, our graph is starting at negative pi over 6. We're transitioning all the way to pi over 2 as we graph this cosine function. And as we transition from one key point to the next, each key point will be pi over 6 units away from the previous one. So knowing what our cycle looks like, where we start, where we end, and knowing how we transition from one key location to the next pretty much gives us everything we need. Now, this is going to be information that is used to label our horizontal axis. Vertically, we don't have a vertical shift, so everything stays centered around the x-axis vertically, but we know we have an increased amplitude versus what the normal cosine graph would have, which would be an amplitude of 1. This is going to affect where our maximum and minimum values hit. So the amplitude of 4 tells us that from the central line, our graph will max out 4 units above, and it'll hit its minimum 4 units below. So before we actually put in the graph, we need to do the hard part, which is generating the labels for the x-axis and the y-axis. Once that's labeled, all we really have to do is put in the standard points for where everything in the cosine graph would be. Okay, so let's start vertically. So let's start labeling where this is and then our max and our min. So again, we don't have any shifts. We don't have a vertical shift anyway, so that means that we're staying along the central line known as the x-axis. So vertically speaking, we're centered at 0. Now again, the amplitude tells us that from 0, we max out at 4, and we hit a minimum at negative 4. So we'll max out at 4, we'll hit our minimum at negative 4. Okay. Now what about our horizontal labels? Well, this is where the cycle and how we transition from one unit to the next is going to be helpful. So our cycle is going to start at negative pi over 6. So here at the beginning of our graph, I'm going to label that as negative pi over 6. That's where we're going to start. Now we then divide our period into 1, 2, 3, 4 equally sized intervals, because again, we transition around the unit circle to generate our points for our cosine graph. The unit circle has 4 equally sized quadrants, so our graph here has 4 equally sized intervals. How do we label these? Well, we know the very last one is going to be labeled at pi over 2 because that's where our cycle is going to end. But what about the ones in the middle? Well, remember, each key location is going to be pi over 6 units from the previous one. So essentially all we have to do is, starting at negative pi over 6, we add on pi over 6 units to go from one location to the next. And if all the math adds up the way it should, we should be able to make it from negative pi over 6 to pi over 2 just by counting with units of pi over 6. Now, you may have to do this written out. That's fine if you do. But in this case, the numbers are going to match up pretty well so that you may be able to do this mentally. So if we were to take negative pi over 6 and add on pi over 6 to transition to the next unit along the x-axis, well, negative pi over 6 plus pi over 6 is just going to be 0. So that adds up nicely. Now again, pretty straightforward. If we were to start at 0 and then transition another pi over 6 units, add on pi over 6, we get 2 pi over 6. Now this might be the moment where you would need to write something down, but let's see if we can do this mentally as well. All we're doing is taking pi over 6 and adding on another pi over 6. So think of it as pi over 6, and then we add on another and we get to 2 pi over 6. So negative pi over 6, 0 pi over 6, 1 pi over 6, 2 pi over 6, which would reduce to pi over 3. And then this is 2 pi over 6, and then 3 pi over 6, which reduces to pi over 2, which is exactly where we're supposed to end. So that's going to be our labeling for our horizontal axis. We've got the vertical axis, and we're ready to go. So all we need to do now is make sure we know which function we're graphing. We're graphing the cosine function, and then we put in the key points for that cosine graph. Now remember, cosine is going to start at its maximum. It drops down to its central line at 0, goes down to its minimum, back to the central line, and then back to the maximum. But don't forget, we have a vertical reflection here. So the normal cosine is going to start at its maximum. Normally the cosine would start at this maximum of 4. We have a vertical reflection, which means it's actually going to flip over and it's going to start at its minimum. So the first point in this single period we're graphing is going to start down at negative 4. And then it's going to transition to its central line. So normal graph, maximum, central line. Well, you can't really flip vertically if you're on the central line, so that point's not going to go anywhere. It's exactly where it would be even if we weren't reflecting. Now, the normal cosine, again, maximum, central line, and then minimum. So we're reflecting, so the minimum point will now become the maximum point. And then we just cycle back, and we complete the period. Okay, we know this graph is going to have a nice smooth wave to it. So essentially just connecting the dots, creating a nice smooth wave. And that is going to be the single period for our cosine graph. Okay, so let's look at the next one. So the next one we had a cosecant, a little bit more challenging. Okay, so what do we know about cosecant and secant? Both of those are graphed essentially the same way. Cosecant specifically is going to be the reciprocal function for sine. So cosecant is very closely related to sine, and their graphs are very closely related as well. So if you remember this technique we used to graph secant and cosecant, we started by graphing the related sine or cosine function. So I'm going to put in parentheses what the related function would be to this cosecant function. Essentially, if we were to keep all of the other values available to us in this function, but just graph the reciprocal function, what would that look like? Well, the reciprocal of cosecant, again, is sine. So we would be graphing y is equal to the sine of pi times x minus 1. So we're going to think of this as the guideline for how we graph. Okay, so graphing this particular function, which is going to be very similar to how we graphed the cosine, is going to give us everything we need in order to graph this cosecant function. Now again, let's start by labeling a, b, c, and d. So in this case, a, the coefficient for our trig function. We don't see 1, so it's an understood 1. b, the value multiplied by x inside of the trig function is going to be pi. C is the number added or subtracted inside of the trig function, and in this case we don't see any, so we know that's going to be 0. And then D is going to be the number added or subtracted on the end, and it's going to be -1. Now that issue with flipping signs that we mentioned in the last problem, flipping signs with C, if it's added, C is negative. If it's subtracted, C is positive. That doesn't apply with D. D is going to keep its sign. So if it's a value that's added, D will be positive. In this case, it's a value that's subtracted, so D is negative. Okay, so we've added in one value that we didn't have before. We've taken one value away. So let's start with the attributes of our function. What about its amplitude? This is one of the most missed problems that anyone encounters on a test. And it's not a trick question, but you have to think about what amplitude actually means. Again, amplitude, like we talked about with the last problem, amplitude is how high or how low you have to get to your graph's maximum and to its minimum. Well, if we think about what the cosecant looks like, when you think back to what the original graph looks like, it's a graph that goes upward forever and ever and downward forever and ever. So there is no actual maximum or minimum for the cosecant or the secant graph. So in terms of the amplitude, this graph doesn't actually have an amplitude. 1 is not the amplitude. If we say that the amplitude is 1, we're saying the highest and the lowest values that this graph reaches are going to be 1 unit above the central line. Well, we know that's not the case based on the shape of the cosecant graph. So the amplitude for this graph, it doesn't have one. We can say none. Sometimes you'll hear it referred to as an infinite amplitude, something to that effect. Now, what does this 1 actually mean, though? It's got to mean something in terms of what the graph is going to look like. We can think of it in terms of the amplitude for the associated sine graph. So I'm going to make a note to the side. The sine graph does have an amplitude of 1. And we're going to interpret that essentially the way we interpreted the amplitude for the cosine graph. Now, what about the period? Okay, period's going to work the same way. We start with the standard period for our trig function, the standard period for sine, cosine, and then their two reciprocal functions. All of those standard periods are going to be 2 pi units. So it takes 2 pi units to get from the start of one cycle to the end of that same cycle. So our standard period is 2 pi, and we're dividing by whatever the value is for b. So 2 pi divided by pi. Well, notice in this case, this reduces. The 2 pi's cancel out. That reduces down to 1, which just leaves us with 2. Now, this is not something we always see. In most cases, when we're graphing in terms of trig functions, we have a period that involves pi. That doesn't mean that we have to every single time, though. So in this case, the pi is eliminated, and our period is an integer. It's a nice clean integer of 2. So that means it's going to take 2 units, not 2 pi, but 2 units to go from the start of this graph cycle to the end. Now, phase shift, that would be generated by whatever value we have added or subtracted inside of our trig function. And in this case, the value is 0. So this graph does not have a phase shift. However, we do have a vertical shift, which we didn't have before. That's going to be our value for D. So our vertical shift is going to be -1, which in this case means we're shifting the graph down -1 units. Okay, so what about our cycle? What do we need to do in order to generate this cycle? Because again, we want to know where's the graph going to start, where's the graph going to end when we graph that single period. So we're going to essentially do it the way we did before. We're looking at the actual input for the sine, and in this case for the cosecant as well. And we want to know how do the things we've done to x affect the standard endpoints for our standard period, which would be 0 and 2 pi. So we're going to set up our inequality. 0 is our standard left-hand endpoint. We're applying these values to our input for our cosecant and for our sine. And we know that that standard period ends at 2 pi. Okay, so how does this affect x, the actual value we're graphing in terms of? Well, we need to divide our pi from both sides. Well, 0 divided by pi is still going to be just 0. And then 2 pi divided by pi is going to be 2. So how does this work with the actual period we found? Well, we found that the period was 2 units. We didn't have a phase shift, which means we're not shifting left and right. We're staying centered right where we normally are. We just shrink the distance that it takes to complete one cycle. Well, it takes 2 units to complete a cycle. We're starting at 0 and we're going to 2, which is a total of 2 units. So that's how the period, and in this case, the endpoints for that cycle are going to match up. Okay, so the only other thing we need to know is what are the landmarks going to be as we transition along the graph of this function. So remember, we're going to take the period, the whole length of that cycle, and we want to divide it up into 4 equally sized parts. So we're taking the full period, divided into 4 equally sized parts, which is going to give us a value of 1/2. And again, what does that mean? That tells us how many units apart each of those key landmarks on the graph is going to be. So that's 1/2 units apart to go from one key value to the next. Okay, and again, now we have enough information to graph everything we need. Now, we're not going to immediately jump into graphing the cosecant. We certainly could, but cosecant is a graph that's not connected. It has separate pieces that aren't connected one to the next. So the way to more easily graph the cosecant or the secant function is to graph the associated sine or cosine. In this case, because it's a cosecant, we're graphing a sine. So we want to actually start by graphing this function. And all of these attributes we've found for cosecant, they're going to be the same for sine with the exception of this amplitude issue. If we're talking about the amplitude for this reference graph, it has an amplitude of 1. So just for a moment, forget that we're graphing a cosecant graph. Imagine we're just graphing a sine. Label your axes based on just graphing that sine function. So vertically what's happening, horizontally what's happening. Okay, so for the sine, for the reference sine, we have an amplitude of 1, which means from the center we go up 1 unit, we go down 1 unit to hit the max and min. But we also have to take into account that we're shifting everything down 1 unit. I recommend when you have a vertical shift, start your graph by working with that vertical shift. So normally our central line is on the x-axis, it's at y equals 0, okay, but we're shifting everything down 1 unit. So where we would normally start at 0, if we shift down 1 unit, the center of the graph is now going to be at -1. Then we apply the amplitude. The amplitude tells us how far up and how far down we go from that central line. So from -1, if we go up 1 unit, that takes us to 0, and that's okay that 0 is above this line. Remember, this line represents -1. It doesn't truly represent the x-axis. This location is now the location of the x-axis. Okay, so 1 unit up and then 1 unit down, which would take us to -2. Okay, now we need our horizontal labels. And again, we know we're starting at 0 and we're ending at 2. We transition around the unit circle to graph this function. So we're dividing our graph into 1, 2, 3, 4 equally sized increments. And we know that we'll start graphing at 0 and we'll end our graph at 2. Okay, and how do we get from 0 to 2? Well, we count by 1/2. Each of these key locations is going to be 1/2 units away from the previous location. So 0 plus 1/2 will take us to 1/2, plus another 1/2, so 0 halves, 1/2, 2 halves, which reduces to 1, 2 halves to 3 halves. You can write it as 3 halves, you can write it as 1.5, your choice. And then 4 halves, which reduces to 2. So there is our labeled horizontal axis. Now I don't want to call this the x-axis, because remember, this is not truly the x-axis. The x-axis is now up here, but this is what we can think of as the central line for the graph that allows us to graph just more normally, based on how we normally draw the shape of our graphs. So again, we're not graphing our cosecant yet, we're graphing our sine. Sine, all of the points we get for that graph, we're going to reference those points in order to generate our cosecant graph. So we want to graph the key points for sine but we're going to graph the sine as a dotted line because it's not really there. It's just there as a guideline for graphing this reciprocal function, the cosecant function. So what do we know about sine? Well, the standard sine graph is going to start at its central line, and then it goes to its maximum, back to the central line, down to the minimum, and then back to the central line, and then that creates one cycle. So we're going to have a point right here for our sine. We go to the maximum, we go to the central line again, we go to the minimum, and then we go back to the central line. And I'm going to connect this with, again, a dotted line because this is just a guideline for graphing the actual function, specifically the cosecant function. Okay, so there we go. So that is not our final answer. What is that? That is the graph of this function, the associated function. So what do we know about cosecant versus sine? Well, let's think about these particular points. Okay, so at this particular location, we're saying the actual function output, the y value, is 0, or excuse me, in this case, -1. But let's think of it kind of like 0. Okay, so if our sine has a value of 0 and we take the reciprocal of 0, we get, instead of 0 over 1, we get 1 over 0, which is undefined. So wherever our sine graph hits this central line, what we think of kind of like 0, we know that the cosecant is going to be undefined. If the sine is 0 and we take its reciprocal, the reciprocal of 0 is something that's undefined. Well, undefined from a graphing standpoint, at least in this case, means that there is a vertical asymptote. So for the actual function we want to graph, anytime our reference graph intersects that central line, we think of it as essentially becoming 0, we know we're going to have a vertical asymptote. So in this case, across this single period, we intersect our central line 3 times. That means there will be 3 vertical asymptotes on this period for this function. Okay. Now that takes care of 3 of the points we graphed for sine. What about the other 2 points, the maximum and the minimum? Well, at this location, for our standard sine, think of that as where the sine is 1 and then where the sine is -1. What happens if you take the reciprocal of 1? Well, you get 1. What happens if you take the reciprocal of -1? Well, you also get -1. So at those locations where we hit a maximum or a minimum, the function and its reciprocal, the sine and the cosecant, are actually going to have the same value. So from a graphing standpoint, what that means is when we hit the maximum and the minimum, we have a shared point between this reference graph and the cosecant that we actually want to graph. So this reference point and this reference point are points that will also be on the cosecant graph. So once we have these 2 points and once we have our vertical asymptotes placed where they need to go, we have curves that emanate from these points and then are essentially just bounded by those asymptotes. And that is the graph generated by the cosecant function. So keep in mind, this little sine wave, this is not actually here. This is a guideline. Technically speaking, there's nothing there in the middle. There's just a hole in terms of the cosecant graph. So these 2 humps, those are going to be the graphs, the portions of the graph represented by the cosecant function. So that will be the standard period for our cosecant function. Okay, let's look at one more. Let's look at our final graph. And this one was a tangent. I wouldn't say tangent is necessarily the hardest one to graph, but we do have to remember something specific about cotangent and tangent because they are slightly different in terms of how we graph them from the other functions, sine, cosine, and then secant and cosecant. Okay, so here's our tangent graph. We have y is equal to the tangent of x minus pi over 4. So let's label our a, b, c, and d. Okay, so a, the value multiplied in front of our function. Again, it's not written, it's an understood 1. Do we have a b? Well, we always have values for all of these, but again, in this case, we don't see anything written, so it also is an understood 1. Now what about our c? So c is the number added or subtracted inside of the function. Remember, the general form contains subtraction. So that means the value being subtracted is a positive number. So in this case, c is going to be positive pi over 4. And then d, the number added or subtracted outside of our function, again, we don't see one, so that means it's going to be 0 in this case. Okay, so let's look at the attributes for this function based on these values. So what is the amplitude? Again, think about what amplitude means. It's how far you have to go above or below the graph's central line to get to the maximum or the minimum. But if we think about what the tangent graph looks like, just standard tangent graph, there is no maximum, there is no minimum. It continues forever and ever vertically in both directions. So for amplitude, it has none. It doesn't have an amplitude. So what does this 1 mean in this case? How do we actually apply that in terms of graphing? Well, think of this 1 as also generating key points above and below the central line that we'll use to generate the tangent graph. So we'll come back to this 1 once we actually start drawing the graph. Now, period. This is where you have to remember something specific. For sine, cosine, secant, and cosecant, those functions all have a period of 2 pi. In other words, you have to transition all the way around the unit circle to get all of the unique values for those 4 functions. Only once you've made a full rotation do your values start to repeat. Tangent and its reciprocal, cotangent, those 2 functions are a little bit different. Tangent and cotangent have periods of pi. Their values start to repeat after only half a rotation around the unit circle. So in this case, our period is going to take our standard period for tangent, which is pi, and then divide by the value for b, whatever's in front of x. Well, in this case, we would just be dividing by 1, and we know that doesn't actually do anything to a value. Dividing by 1 doesn't change anything. So that means our period, how far it's going to take horizontally to start a cycle and end it, is going to be pi units. Now what about our phase shift? Remember, we get this from c. It's c divided by the value for b. So it's c, which is pi over 4, and again b is just 1. We divide by 1, nothing happens. So our phase shift is going to be pi over 4 units. Now because this is positive, this is going to shift to the right. And again, how does this match up with what we see in the actual function? Well, subtraction tells us we're shifting in the opposite direction. We're shifting in the positive direction, hence the positive value for c, the positive phase shift. What about a vertical shift? Well, again, we don't see a number outside of the trig function, so we do not have a vertical shift. There is none. So the only thing that actually changes for this particular function versus the original tangent function is that we're shifting each of the key locations on the graph pi over 4 units to the right. Okay, so I'm going to star this, and I'm also going to star this, because these are 2 special things that apply to tangent. The period is different than what we see for our 4 other trig functions, sine, cosine, secant, and cosecant. And how we generate the cycle is also different. And we talked about this a good bit in the graphing video for tangent. We talked about how you graph tangent because the cycle is a little bit different than what it is normally. For the other 5 trig functions, the standard period is going to start at 0. But when we looked at tangent, we encountered a slightly different issue. When we started at 0, we ended up with a graph that didn't really demonstrate what the tangent looks like, what a single period of the tangent looks like, because it breaks up things if we just start graphing at 0. So rather than starting at 0 and graphing a full period from 0 to pi units, we actually started the tangent graph at a different location in order to get one full branch of the tangent's graph. Rather than starting at 0, we started at negative pi over 2. We started a little bit backwards of where we normally start, because starting there is going to allow us to generate one full branch rather than 2 half branches for our tangent graph. So the period is pi. In other words, we go from negative pi over 2 on the left 2 pi units away, which would be positive pi over 2 units on the right. And again, we want to see what's happening inside this actual tangent function and how does it affect those endpoints. So negative pi over 2 on the left, and then we are applying this particular transformation to x, and then our standard endpoint on the right would be positive pi over 2. And again, if you notice how far apart these two values are, those are going to be pi units apart. Okay, but we want to see what happens based on this fact that we've subtracted pi over 4. How does this affect these two endpoints and where we start and where we finish our graph? So I'm going to add on the pi over 4 to each of these endpoints. Now, you may want to get the common denominator. So negative pi over 2, if we want to add on pi over 4, we could call this negative 2 pi over 4. And if we add on a pi over 4, that's going to take us to negative pi over 4. It's still a negative number, but it's not as negative. It's further in the positive direction, hence the shift to the right. Same thing over here with positive pi over 2. If you need, think of this as 2 pi over 4 plus pi over 4 would give you 3 pi over 4. So that's going to be our new right-hand endpoint. Okay, so the only other thing we need to know, again, is where do we hit our landmarks? And again, we're going to divide our graph up into 4 equally sized increments, okay? Starting from negative pi over 4, going to 3 pi over 4. And again, it's going to take our period, and it's going to divide it into 4 units. So pi divided by 4. And that's going to be the number of units apart each of our graphing landmarks is. Okay, so we have everything we need. We know where our graph should start, we know where it should end, and specifically for our tangent graph, these two values are going to represent the locations of our vertical asymptotes. That's also why we start by graphing from negative pi over 2 to pi over 2 for our standard tangent graph. This is going to be the location of a vertical asymptote. This is going to be the location of a vertical asymptote. If you started at 0, you're starting halfway and then you're having to jump over an asymptote rather than just graphing something that stays between two asymptotes so we get the full picture. So these are going to be the new locations of the two vertical asymptotes for this particular tangent. And then again, we're going to divide things into 4 equal parts. How does the amplitude affect everything here? That just tells us where we're also going to have some key points. We're going to have key points 1 unit above the central line and 1 unit below the central line as well. So let's label everything. Let's start vertically. So we haven't shifted vertically, so our central line is still at 0. And again, we have a key point 1 unit above, we have a key point 1 unit below, so at 1 and negative 1. And then again, we are starting our cycle at negative pi over 4, and then we're transitioning to 3 pi over 4. So negative pi over 4, and then 4 equal increments. And I'm spacing these a little bit closer together so that we can graph a little bit more nicely than we would do with the others. For this one, the graph doesn't really stretch. It's going to be kind of compressed together. So I would graph these a little bit closer together. So we're starting at negative pi over 4, and we know we're going to end at 3 pi over 4. Okay, and in between, we're transitioning by pi over 4 units to go from one key location to the next. So negative pi over 4 plus pi over 4 is going to take us to 0. Okay, plus another pi over 4 takes us to pi over 4. So negative pi over 4, 0 pi over 4, 1 pi over 4, 2 pi over 4, which reduces to pi over 2, and 3 pi over 4, which is where we're supposed to end. So that looks good. Okay, so by setting up this inequality the way we did, again, we found the locations of vertical asymptotes, locations where our tangent is undefined. So on the left-hand side, the left-hand endpoint, we have a vertical asymptote, and then we also have one on the right-hand side. So what's happening in the middle at these 3 key locations? Well, in the very middle, that's going to be where we intersect our central line. Okay, and on one side we're going to be above the central line, on one side we're going to be below the central line. Now, how do you remember which is which? One way to think of it is if you look at the unit circle, what's happening to tangent as you transition around the unit circle. In other words, as your x values increase or your radian measures increase, what's happening to the value of tangent? Is it getting bigger or is it getting smaller? Well, tangent's going to get larger as we go around the unit circle in the positive direction. That means tangent is an increasing function. The cotangent, on the other hand, is going to get smaller. It's going to decrease. So tangent is going to be an increasing function. It increases left to right. Cotangent is a decreasing function. Otherwise, they're going to look pretty much the same in terms of the shape you graph. So tangent, as we go from left to right, it goes from smaller values to larger values. That's where this -1 and this 1 are going to come into play. So our other two key locations, those are going to be locations where we hit -1 on the left and +1 on the right. And past that, it's just a smooth curve that's bordered on the left and the right by vertical asymptotes and then passes through these 3 key points. So that is going to be our graph. Okay, so if you missed the graphing problems, even if you got some points for it, I definitely recommend that you go back and you practice graphing these. You will have to revisit these problems at a later point. Being able to graph these pretty flexibly, pretty easily, understanding how these parts really fit together is going to be important. So definitely spend some time watching this video. Go back and try to graph on your own. If you get stuck, again, come revisit the video. And of course, let me know if you have any questions.